So note that this is a parentheses at the beginning and at the end. So that means we don't have to consider the left and the right endpoints as potential local extrema. Okay. So our goal here is to find values of x that reach a local minimum or a local maximum. And those things happen when the first derivative equals 0, and that means it's a potential local maximum, local minimum. It's not guaranteed. It means it's the only, with the first derivative equals 0 or the first derivative fails to exist, those are the only places where we could potentially have a local max. Or those are critical points. Okay, and like I said just a second ago, critical point. Remember, just it's not guaranteed to be a local max, local min. You got to test it out first. So let's go find that derivative. So the derivative of f of x using the quotient rule, it's a derivative of the first function. So that's 5e to the 4x, because the derivative of an exponential function is itself times a natural log of the base, which would be natural log e. So that's why it's just itself. But because of the chain rule, we have to multiply this by 4 on the outside. So that's a derivative of the numerator, and then the denominator stays the same when we use the quotient rule, the first part, the first term. Then we subtract that by the original first function times the derivative of the second function. That's all over the denominator squared. So we've got to clean that up a little bit. And then here, that's 5 times 5 makes 25. And then in the numerator, we can factor out a 5 and an e to the 4x. So that'll make our lives a little bit easier. And what we have left over, this first term, when you factor out a 5, 20 divided by 5 makes 4. And you factor out the e to the 4x, so you're left with 5x minus 3. Then here you factor out a 5, so that's 5, that's it, 5 is just left over, right? 25 divided by 5 makes 5, e to the 4x divided by e to the 4x makes just 5 here. Okay, and then the denominator is still 5x minus 3 squared. So critical points are places where the derivative equals 0 or where the derivative fails to exist. So clearly we have a divide by 0 problem if we had 3/5 in here. But we don't have to analyze 3/5 because it's not between these two numbers. 29 divided by 40 makes 0.725. So we don't have to worry about that part. Instead, what we can do is we can go try to find the other critical points, the ones for x that would make it equal 0, make the derivative equal 0. So we want to multiply both sides by the denominator. That's just going to cancel it out, right? 5x minus 3 squared, you multiply that to 0, just makes 0. So down here when we simplify, that's 5e to the 4x. And then if we simplify in here, that's 20x minus 12 minus 5. 20 minus 12, yeah, okay. And then simplifying a little bit more, that's 20x minus 17. We want to set this piece equal to 0 to find out where the derivative equals 0. So if you solve that, you get x equals 17 over 20. Again, I just set this equal to 0, did some quick mental arithmetic to solve that equation. You'd also want to see what it takes to make this piece equal 0. But e to the 4x, can you put a number in for x to make this circled piece exactly equal 0? The limit as x approaches negative infinity might work, but we're talking about a specific value for x. Infinity isn't a number, okay? So there's no value for x that you can plug in here that would make it equal 0. So we found one critical point, x equals 17 over 20. So to find out whether 17 over 20 is a max or a min, we can use the first derivative test. And what the first derivative test does for us is it says, hey, you got a function that looks something like this. Well, look, it's a maximum. It's a local maximum. If a value directly to the left, between any two, make sure you don't go past any critical points when you pick that value. But if there's a value to the left that has a positive slope and a value to the right has a negative slope, then you've got a local maximum. And then likewise for local minimum, if your derivative to the left is negative, but your derivative to the right is positive, you've got a local minimum. Okay, so we want to look at the derivative directly to the left and directly to the right. And I don't want to go outside my interval. So what's 16 over 20? It's 0.8. Yeah, let's test the derivative at 16 over 20. That's something to the left. And then how about x equals 1? Oh, wow, that's wrong notation. That would be the y value. We want the x value, 16 over 20. Something to the left of 17 over 20. And then something to the right of 17 over 20, let's plug in 1. If this is positive and this is negative, then we know we have a maximum based on that anecdote I just gave you with that graph. If this is negative and this is positive, then we know we have a local minimum. Okay, there's our derivative. Man, plugging in 16 over 20 is going to be a chore. Oh, that's not so bad. So plugging in 0.8. Let's copy that to the clipboard. And so, oh, it is going to be a chore. Why? So let's just take it one step at a time. So in the numerator, in the exponent position, 4 times 0.8, we want to take e to the power of 3.2. So e to the power of 3.2 times 20. So this part right here, 20e to the 4 16/20 is 490.65. And then if we do 5 times 0.8, 6.25 minus 3, so that makes 3.25. And then here we got to do the same thing over here. This is probably would have been easier to use the factored form, huh? 0.8 times 4. We want to take e to the power of 3.2 times 25. Makes 613.313. That's all being divided by. Plug in 0.8 into the denominator. 0.8 times 5. Yeah, that makes sense. Minus 3 squared. Okay, they had some mercy on us, the denominator. Almost done. Well, we can actually stop because we're really just interested in the sign, not what the particular value is. It's definitely going to be positive, right? We got a positive derivative. So we can say that this derivative is greater than 0. It's positive. Remember what we said with that graph. If it's positive up until you hit the critical point, and then it's negative on the other side, then it's a local maximum. So we need to find out what happens if we plug in 1. If you plug in 1 into this thing, it's 20e times 5 times 1 is 5. 5 minus 3 is 2. Minus 25. Sorry, that's e to the 4th power. That's minus 25 e to the 4th over 5 times 1 minus 3 squared. Minus 25 e to the 4th, so that's 15 e to the 4th. And then down here, 5 times 1 is 5. 5 minus 3 is 2. 2 squared makes 4. So it's positive. We get something here. Let's just say it's positive. If the value to the left and the value to the right are both positive, then this is neither a local max nor a local min. The derivative has to switch. But I just jotted this down on pen and paper, and I got something plugged in wrong over here. So 16 divided by 20, that was 0.8. 0.8 times 5 minus 3. Yeah, I messed this part up right here. That shouldn't be 3.25. That should be 1. So that one little mistake, 490. That's roughly 490 subtracted by 613. So that's going to be a negative number. So I got this part wrong. That should be less than 0 when I plug that in. Look, if a derivative to the left of your critical point is negative, that means it looks something like this. It's going down. Negative slope. We tested it. We found out a slope a little bit to the left of the critical point is negative. A slope a little bit to the right was positive. So it's making a local minimum. So for this question, x equals 17 over 20 is a local minimum. Same thing with this problem. To find local extrema, we want critical points, so we take the derivative. So you want to check what I did here. Power rule just makes -3. The derivative of natural log 3x is 1 over 3x, and then times the derivative of the innermost function. So that's, I forgot the 4 on the outside. 4 times the derivative of natural log, that's 1 over 3x, but then times the because of the chain rule, multiplied by that 3 on the inside. So that's how I arrived at 4 times 1 over x. Technically, the derivative fails to exist at x equals 0 with the way it's defined right here. Plug in 0 in for the derivative, and that's because, look, if you plug in 0 right now, you got a divide by 0 problem. So critical points are where the derivative fails to exist, or where the derivative equals 0. So quick little algebra equation. That's like a catchphrase of mine, isn't it? Quick little algebra equation. Not super cool, am I? So x is 4/3. So there's our other critical point. We want to analyze both of those using the, I think it said the first derivative test. Yeah, so we'll do the same thing we just did in the other problem. So 4/3 and 0. Oh, but it says on the interval 1 to 3. So ignore the 0, because that's not on this interval. 0 is on the outside. So the only critical point we want to analyze is the 4/3. So we want to check the derivative to the left. So I'll do 1 because that's nice and easy. And a derivative to the right. 2 is to the right of 4/3, and it's within our interval. Yeah, I deleted the derivative. Okay, so if we plug in 1 into the derivative, get -3 plus 4, so that makes 1. If you plug in 2 into the derivative, get -3 plus 2, so it makes -1. So the slope is positive. Here, let's say this is the critical point. Oh, it doesn't. Here, let's draw it without it. Slope is positive 4/3. Let's do it over here. We tested a point slightly to the left. We got a positive slope. We tested a point slightly to the right. We got a negative slope. So that means we're going to reach a local maximum. Okay, so 4/3 is a local maximum. There's no local minimum. Okay, you know the drill. It's just a trig function, but it's the same process. We want to set the derivative equal to 0, or find out where the derivative fails to exist. So the derivative of cosine is negative sine. That's a derivative of the outermost function. And the derivative of 4 is going to be 0. But actually, we're not done this one. The derivative of cosine is negative sine. But the derivative of the innermost function is 2. So we got to chain that on. And the derivative of minus 4 just makes 0. So this is -8 sine 2x. We want to find out what it takes to make this equal 0. Okay, so what you want to think about are the values of sine, so the angles that would make sine be 0. Sine is 0, sine is the y coordinates on the unit circle. So we get sine, a 0 value for sine when x equals 0, when we make no rotation, because that's 1, 0, when x equals pi, or if you do a full rotation, when x equals 2 pi, or when x equals 3 pi. I had to think for a second. And it can keep going on and on like that. So what we want to be able to just plug in a pi in here, and that would make this equal 0. So we want to solve a mini equation. We want to find out what 2x equals 0. We want to find out what x would be in order to make our sine equal 0. And we want to do the same for all the other ones. 2x equals pi, and check all the other ones. 2x equals 2 pi, and 2x equals 3 pi, and we can keep going like that. But we just need to watch out for an interval. X needs to be between 0 and 2 pi. So if you solve this equation, then x equals 0, but we don't include 0 in our interval, so we won't consider that a critical point. X equals pi over 2, if you solve this equation. X equals pi, if you solve the next equation. And x equals 3 pi over 2. We're getting close to the edge. You can probably guess if you tried the next one, 4 pi, which would just mean 2 full rotations, that brings us back to a y coordinate of 0. And so if you solve that equation, you get x equals 2 pi. So this one's out and this one's out because it's not brackets on this interval. These are the 3 critical points we need to test. So I circled our critical points over here and made a quick little number line. What we want to do is we want to test what the derivative is slightly to the left and to the right of each critical point. So here I'll pick a number that's on my interval, 0 to 2 pi. Let's plug in pi over 4. That's something slightly less than pi over 2. We're plugging that into the derivative, right, because we're using the first derivative test. And then something slightly to the right, but it's got to be between these two. So how about 3 pi over 4? 3 pi over 4. That's to the right of pi over 2. That's to the left of pi. And if we plug in between pi and 3 pi over 2, how about 5 pi over 4? And I'm just trying to pick numbers that are going to be easy for me to calculate here. You can pick any number you want between pi and 3 pi over 2. And then here, at x equals 3 pi over 2, we need something slightly to the right. So continuing with our denominator 4 pattern, needs, would that be 7 pi? 7 pi over 4. That's slightly to the right of 3 pi over 2, but it's not above our interval. So we need each of these derivative values. So when you plug in pi over 4 into your function, into the derivative, pi over 4 times 2 gives you pi over 2. Pi over 2 lands you here in the unit circle. That value is 1. So this is 1 times negative 8. We get negative 8 for that first derivative. So 3 pi over 4, if you plug that in for x, oops, I don't know why I keep pointing at that one up there. 2 times 3 pi over 4 gives you 3 pi over 2. So this is pi over 2. That's 2 pi over 2. This is 3 pi over 2. That gives you a negative 1 on for a y coordinate. Because remember, sine is the y coordinates in the unit circle. So negative 8 times negative 1 gives us positive 1. 5 pi over 4, if we plug that in for x into the derivative, that gives us 5 pi over 2, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 4, that's not a circle anymore, 4 pi over 2, 5 pi over 2, the corresponding y coordinate is 1. So negative 8 times 1 gives us negative 8. And then the last derivative we need to test right here, 7 pi over 4. If you plug that in here for x, 2 times 7 pi over 4 gives you 7 pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5, 6, 7. We get out a sine of 7 pi over 4 is a negative 1. Negative 8 times negative 1 gives you positive 8. Okay, now we're ready for the max and min stuff. We went from a negative, oh, is this right? 3 pi over 2, that's 3 pi over 2. Oh, I messed that up. That should be a positive 8, not positive 1. Okay, that doesn't change the answer though. Go from a negative to a positive. That means you went all the way low as you possibly could, and then you started increasing after pi over 2. So pi over 2 was a minimum, just like we saw in the other problems. So positive 8 to negative 8, you hit a maximum. You were at the peak, and then your slopes turned negative, and you start decreasing. So pi is a max. And then we got a negative slope to the left of this critical point, a positive slope to the right. So we went from negative to positive. That means you hit another minimum. So 7 pi over 4, is that one of the ones we got? Oh, no, sorry, this is a critical point. 3 pi over 2 was also a minimum. So these are our minimums, this is our maximum.